All right, folks. I am in a hotel room. It is 8 o'clock in the morning, and I would really rather be with y'all giving you this talk, but I can't. So I'm recording this over Zoom, and a little sad because I really like to have questions and interact with folks while giving a presentation, but there's Slack. You can always Slack me or email me any questions afterwards, or if you see me around this week, you can definitely chat as well. Okay, so today I am going to tell you a little bit about supermassive black holes in the context of galaxies. So you've heard a lot about data analysis. You've heard a lot about supermassive black holes and the way that they make gravitational waves, but I want to tell you a little bit about how supermassive black holes act in the wild. So in fact, that's the title of my talk. So here we go. Alrighty. So I'm just going to get started and let you know that there's a problem with black holes, and I'll explain a little bit more carefully. But this is a really lovely image of one of the furthest quasars, and in fact, JWST is going to find a whole lot more distant quasars. But Jesse and Maria are going to talk to you about observations of these types of quasars. What I do want to show you is these are up top, they're photometric images, and what you can see is just like there's basically nothing there in the sort of red optical bands, and then you start to see a lot of photons in the infrared, and that is because of redshift. So here is a spectra. This is flux as a function of wavelength, and we're zooming in on a particular line here, and that is the carbon-2 line, and its rest wavelength is 158 microns, and you can see it here highly redshifted. And given that, you know that this quasar is about redshift 7.6. Okay. So it doesn't look like a lot photometrically. It's gorgeous spectroscopically, but it's a big problem. And that is because of the time of the universe and how we think black holes accrete. We don't really know, but there's this toy model that says that basically anything, be it a cheeseburger or a black hole, has this maximum amount of light that it can emit before radiation pressure pushes that matter away. So there's this battle between gravity that wants to pull matter in, and radiation pressure, which wants to pull or push matter out. And I can derive this for you. I don't have time right now in this sequence, but I'll upload something that goes to this a little bit more carefully. But nonetheless, this process is called the Eddington luminosity, and it is the maximum energy output of a black hole. I put maximum here in a star because there's a lot of caveats here, and I want you to know that the caveats are really important. So I'll get to them in a second. Okay, but nonetheless, this is the luminosity that can be made by a black hole or a cheeseburger or whatever. This is the mass of that black hole, mass of the proton, and this thing is called the Thomson cross-section. It is essentially the effective area that an electron presents to the world or to an electromagnetic wave. Okay, so this is the amount of energy that can be made by anything that has matter, the maximum amount. And this is the amount of energy output that can be made from converting potential energy of matter onto, in this case, a black hole. And so this is the mass it is the mass accretion rate, speed of light, and this little epsilon is an efficiency factor, which I will get to in just a second. So you convert potential energy into light, but there's a maximum amount of light that you could make. And so you can equate these to figure out what the maximum rate of growth of a black hole is, okay? And that solution is this. So the initial mass of a black hole can grow exponentially and with time. And this is a characteristic time scale here called the saltpeter time. If you're an astronomer just kind of pulling a number out of the air, it's 45 million years. Note that it's got a little epsilon here. So it depends upon the efficiency of converting infalling matter into energy. So here we go. Note that if you have matter falling in from infinity and accreting in a thin disk, then the efficiency factor is about 8%. Compare that to the PP chain, the thermonuclear fusion of hydrogen into helium in the center of a star that has an efficiency of about 7%. So not bad. But if you have matter that is falling in at ISCO around a maximally spinning Kerr black hole, that's 42%. So 42% of that infalling matter gets converted into energy. And there is a huge range here, right? And so astronomers pick an epsilon of 0.1 just because you will see this happen a ton of times in theoretical work. And folks will just choose a number that's kind of in the middle or even-ish with 1 sig fig, just to show you that we don't really know what we're talking about quite yet. And we're tucking a bunch of uncertainties in. And just this is part and parcel why a lot of theoretical estimates are not quite wrong, but estimates, right? And it's fine for a lot of astrophysics because we can't measure a physical quantity like the mass of a black hole to the accuracy of, without gravitational waves. It's very difficult to measure the mass of a supermassive black hole accurately enough for epsilon to really matter. But pretty soon we're going to have to start worrying about that. A couple of things I wanted to let you know about this whole scenario. Not only do you have to worry about that epsilon not actually being right, but this assumes that energy is that the matter is just distributed spherically, that it is hydrogen, and that it's these simplifications cause a big problem. But assuming this nonetheless, there is barely enough time to grow the black hole that we just saw at redshift 7 here, 7.64. So what you're seeing here is the mass of a black hole and solar masses as a function of redshift. This is redshift 30. We basically haven't seen anything past 10 electromagnetically. So yeah, this is sort of there'd be dragons here. But here is the time scale since the Big Bang. So we see, 700 billion years have, 700 million years have just passed since the Big Bang. And this is that saltpeter exponential growth by assuming the Eddington rate, assuming an efficiency factor of 0.1, that the matter is hydrogen, that the radiation pressure couples with electrons, so we're dealing with Thomson scattering, that everything's spherically symmetric. So assuming all those things, then in order to get the mass that we see at redshift 7.64, you had to have started with a black hole really early in the universe at redshift 30, before we think galaxies form, although we don't know for sure, before the first stars form, or maybe commensurate with that redshift, although we don't know for sure. But anyway, you have to start with a black hole that is 10 to the 4 solar masses, so pretty big black hole in the first place. This rules out a lot of other black hole formation scenarios, which we'll get into in a little bit. So that is an issue, and it's an issue that folks are struggling with now. But I think Personally, I think the answer is we just give up on this Eddington rate. We give up on this concept of accreting forever at the Eddington rate. There can be episodes of super Eddington accretion if we just relax some of these assumptions, mainly spherical symmetry. I think we'll be okay. Still, you'll hear people worry about this for a while. Still. Okay, so now I want to talk to you about, we've sort of said black holes already are an issue given that they're at high redshift, but I want to talk to you about how they affect galaxies and even the universe. These are on scales that are way, way larger than what you've dealt with in this workshop before. You're used to dealing with things where space-time is not perfectly flat. Relativity sort of matters. Here, we're talking about physical scales that are 12 orders of magnitude larger than the black hole itself, than ISCO, or the Schwarzschild radius even. Those are about the same according to my book, because we're dealing with physical sizes that are so much larger. So a black hole, even though it is 12 orders of magnitude smaller and 6 orders of magnitude smaller in mass, can have a dramatic effect on the galaxy, as we'll see. Okay, so the biggest deal, the reason why black holes have such far-reaching effects is because they have this process called feedback, which is when matter falls into a black hole, again, you make energy. Some of that energy goes into photons that heat up the gas around the black hole. And by around, I mean it can be, thousands of parsecs. Sorry, parsecs are 3.26 light years, and a light year is what, 6 trillion miles or 9 trillion miles. Anyway, they are about 1 million times larger than 10 to the 6 solar mass Schwarzschild black hole. Anyway, huge distances. That's nearby, according to an astro. Okay, so anyway, the material that falls in can heat up, and those photons can travel into the gas and heat up that gas, prevent it from cooling, and so that prevents star formation from forming. That's called thermal feedback. But you can also have mechanical feedback from jets, and the jets can, or outflows in general, can literally push the gas and evacuate the gas entirely from a galaxy, and that can stop star formation as well. Here's a nice picture by a simulation from Michael Tremmel that shows this process, both of them, in fact. So black hole is here, and all we're seeing right now are the gas temperatures in the colors. So you can see that 10 to the 8 Kelvin, 10 to the 6 Kelvin. Here's the darkest right there. And these little lines are velocity vectors, and the largest velocity vector, well, here is the size of 1,000 kilometers a second, which is crazy pants fast. It's faster than the escape velocity of the Milky Way, for sure. And so this is the directionality, and the larger the arrow, the larger the magnitude. And so you'll see physical outflow, this mechanical feedback happening right here along something that looks like a jet. You'll also see thermal feedback kind of in the same region. Here is still pretty hot gas, 10 to the 6 solar mass, 10 to the 6 Kelvin gas is much hotter than anything that could form stars. But you see really super hot gas basically everywhere, especially along this jet-like region. And that has a consequence. These are observations rather than simulations, and they're of galaxy clusters. And so this is in the X-ray here, and what we're seeing is this Perseus galaxy cluster. This is 20 kpc, which is about the size of the whole Milky Way disk. And you're seeing the center of that galaxy cluster. There's a large galaxy there, Perseus A, and it's got a supermassive black hole in there that sinks 10 to the 9 solar masses, I think. And anyway, it's accreting, and therefore it's heating up the surrounding gas, and it's also pushing the surrounding gas. But this cavity here, are all to do with basically evacuating the gas. So that really does happen. And here we're seeing an overlay of X-ray and also radio waves. So you'll just see here this sort of cavity shape. That's really all I wanted to show you about that. And it's in a galaxy cluster as well. Here you can also talk about outflows. I think I'm just showing you this slide because I like that little picture. Just to reiterate the process, you can have a black hole here. Stars are forming around it. The accretion sort of blasts out the gas. And if there's no gas, you get no more star formation. And that gas around there can obscure the black hole. Now, Jesse's going to be talking to you, and Maria are probably going to both talk to you about that. But if they don't, it just means it's not well seen in invisible light. Anyway, and then you have a black hole that's not accreting anymore because there's no more gas around it, and the stars are also basically old. So this process is called quenching, and it's quenching from feedback. Here's an old simulation by now that shows this process. These are two equal mass galaxies, and what you're seeing are the gas here, and the temperature of the gas is the color. And you'll see in just a second that there's going to be kind of outflow and a different color there. You can start to see a little bit of gas heating. There's black holes right in the center of these, if I didn't mention. And you're seeing a lot of mass accretion and therefore a lot of feedback. And a train wreck for a little while, giant more feedback once the two black holes get pretty close to one another, and you basically have obliterated the galaxy. Now, this was actually a really famous simulation. DiMatteo and Volker Springel did it, I think 2001. It is wrong. Nothing against them. It's just that you can kind of tell it's wrong because the whole galaxy is obliterated by this process, and you get this instantaneous explosion of the galaxy due to feedback. And this is a common problem in simulations, even after this. We can't implement properly feedback. We can't actually implement the proper physics of mass accretion onto a black hole, again, because the physical sizes are so different. So we put these subgrid physics modules in to mimic the effect of black hole growth and black hole feedback. And it has a tunable parameter, kind of like that epsilon. And we're not kind of ever getting it perfect. So it is not uncommon that feedback will be really too strong in simulations. To be continued. This is a solvable problem, I think. Okay, so but these outflows from AGN feedback, from supermassive black hole feedback, can totally affect the entire galaxy. So here's an example of that. Here's feedback only from star formation, from supernova explosions. So that is a set of simulations here that were mergers. These are minor mergers. So a minor merger came in, you're seeing the top, down, and side view of these types of galaxies. This is sort of a medium merger, and this is a major merger. So minor merger, major merger. And this is with just supernovae. And here's that same galaxy simulation that adds black hole feedback. And in a minor merger, it doesn't really affect much, although you can see some gas flowing out. You can see that the center is it's a little bit different, has less gas around. But the major merger, look here, you turn a disk into an elliptical. Okay, so this concept has been shown over and over and over in simulations. Maybe the feedback's too strong, but nonetheless, the process seems to be consistent. You have a black hole, that black hole accretes, it heats the gas, it blows out the gas, it quenches star formation, sometimes quickly, but what is left is this galaxy that is called red and dead, meaning the stars are old, and there's no more star formation left, and usually an elliptical, but not always. Okay, I didn't write right here, so you'll just have to listen. Okay, so we have this idea that black holes can quench star formation, and that is a really well accepted idea. However, really recently, folks have realized that shocks from the outflows of an accreting black hole can hit ambient gas, and if the ambient gas is a lot, or if there's a lot of ambient gas, sorry, let me try and do English, then the black hole can excite star formation. So it kind of does both. And here's an observational picture. It's a composite, so just hold on. This is the black hole, and it's got jets here. You can see them there in purple, and then here's the other side of the jet. And you're also seeing, and so this is in radio. This is X-ray data that just shows, oh yeah, this jet is also heating. However, right here are a bunch of galaxies that wouldn't have been star forming, but now have been triggered to start to form stars because of this blast wave of material that excites star formations in sort of pressure-driven star formation, is what folks call it. Here is kind of another example. Really recently, see all this galaxy wasn't discovered by this author, but there's another paper similar to that. Okay, so this is a nice little spirally galaxy, has a black hole in it about as massive as the Milky Way. We're zooming in. And now we've got the model that can explain this, which is there's material going out from this black hole. In this region, you heat enough provide enough energy to sort of ionize all this gas. But the physical outflow can slam into overdensities of gas nearby, and cause star formation. So we're seeing that happen. We're seeing it happen in simulations too. I don't remember if I have it. No, but there's a couple simulations that that are starting to show this as well. So black holes can regulate star formation, and usually back in the day, folks meant by regulating it means it turns it off, but or quenches star formation. But now we know that black holes can actually excite star formation too. So it does both, but on scales that are way, way, way larger than the black hole itself, on galactic scales. On extragalactic scales, early on in the universe, we have this the cosmic dark ages, folks call it, and that is because we have neutral hydrogen around, and when there is any photon emitted, the photon mean free path is very small when it interacts with a hydrogen atom and maybe reionizes it. And once it does that, then the photon has a larger mean free path and can come to our eyes. But we need that heat source to ionize the universe. And this is a lovely simulation. I'm showing it to you just because it's pretty. So it's a box of the universe. And what you can see are these little Swiss cheese things of supermassive black holes and the first stars radiating away their energy and kind of, ionizing the region around, sort of ablating any neutral hydrogen around until you can start to peer in to deeper into the universe. So it's a lovely, this is Tom Abell's work. Okay, so we've talked about the fact that supermassive black holes are really quite large at very early times, that requires a birth mechanism that is non-trivial, and also a growth mechanism that seems to be continual and at maximum, or more than maximum if you want to give up the Eddington limit approximation. So let's talk about how black holes are born. And there's a ton, we don't know for sure. You can form them from the first stars. Okay, we'll not talk about that so much. You can form them from just gas in a dark matter halo collapsing and directly forming into a black hole. That's this one. Or you can talk about forming a really, really dense and unstable stellar cluster, and those stars kind of collapse in upon themselves and form a conglomerate wad of stellar black holes that form into one. There we go. Yeah, so we're going to talk about this one. And this one makes what are called the heavy seeds. I'm going to go back. This formation mechanism from the first stars makes very light seeds, about 300 solar masses, couple hundred solar masses. And these direct collapse black holes can form 10 to the 4 to 10 to the 6 solar mass black holes. So let's go with that, because we need to make these quasars. Okay, so the problem with black hole formation in general is that you need matter to fall in, become really dense, and so dense that you make a black hole. Great. However, the conditions for star formation are kind of similar. You have overdensities in matter that collapse and then form a star. And the difference is that in the star formation arena, you have overdensities that are rather small because the gas cools very quickly, and then the overdensities fragment away from the rest of the cloud. So they decouple from the cloud, and then they can collapse under gravitational forces. It's the Jeans mass. The Jeans mass ends up being rather small because just that little piece becomes collapsible. Here's an example of that. These are the first star simulations by Matthew Bates, and you can see we've got a couple snapshots, and you can see densities here that are quite high, 10 to the 16 particles per cubic centimeter. And there, Matthew is kind of noting overdensities here. You're starting to form another kind of overdensity here, which does collapse to form a star. And then it looks like there's 4 stars. I'm counting 3, but I bet you there's just one over plotted with one. After 110 years after the epoch of the first star forming, you get a couple stars. But just kind of notice how there's small fragmented overdensities here. Not a good thing for a black hole. If you want a black hole to form, you have to battle that fragmentation. You need to keep the entire reservoir of gas at about the same temperature and allow it to collapse gently until it reaches this overdensity, the whole thing, to make a black hole. Okay, so in order to do that, you have to battle cooling. You need to keep the gas warm. And there's a bunch of ways to cool the gas. You can have metal line transitions, which if you have an electron jump up to a higher orbital in any kind of atom, including a metal, then once the electron goes back down to a lower state and emits a photon, that photon leaves. And so that is energy emission, and then the gas will be cooler. So here is that concept of the cooling rate of gas. So how effective a particular gas is as cooling as a function of the mass of the dark matter halo. So these black holes form in a dark matter halo, and so this is trying to tell you about the mass of that typical black hole. Typical dark matter halo. Okay, so this says that metal cooling is way over here, and it's really, really effective. So once you have metals in a dark matter halo, then all bets are off. You make stars. You make stars. You don't make black holes, according to these this theoretical picture. Oh, by the way, metals are anything more massive than helium. So carbon is a metal in this case. Sorry. All right, so you can also have atomic hydrogen blind cooling, and that is effective for these mass halos. So if you have these mass halos, then you have the gas active enough so that you can excite atoms, hydrogen atoms, to go to a higher state. And then once they de-excite, they can emit photons and cool. So atomic line cooling means that in this region, the neutral hydrogen is effective at making stars rather than black holes. And here, there is atomic line cooling. Notice it's not as efficient, but remember, molecules have a bunch of ways to release energy. They can sort of vibrate or rotate in addition to the electronic orbital levels. So again, if you're in this massive halo and you have molecular hydrogen in this center region, then you'll form stars rather than black holes. So we don't want any of that stuff happening. We want the gas to be able to cool gently and not fragment and form a black hole. Okay, so here's the idea. You can have one of those molecular hydrogen halos, these kind of lower mass halos. And if you just had a way to bust up the molecular hydrogen, there's the halos are not massive enough to excite the atoms, the hydrogen atoms, so you can't cool this way in this region, or at least not effectively. So this would be a lovely region to form a black hole if we could only bust up that molecular hydrogen, and it turns out we can. So if you have the first stars or accreting black holes, then there is enough radiation to bust up molecular hydrogen. Okay, so what the energy range for busting up molecular hydrogen is this, 11 to 13 eV, okay? You need that. And it turns out the first stars emit a flux of that particular wavelength band that is larger, how about I just say it that way, than black holes. But nonetheless, both create this type of energy that is a molecular hydrogen buster. Once you have those molecular hydrogen molecules disassociated, then the gas can cool gently. Again, the gene's mass is large, and you can form a massive black hole. Here's a cute picture of the problem, though. Okay, so this is a schematic. And we have here these little circles are dark matter halos. And so there's a dark matter halo here, 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 here. And in this dark matter halo, we have the very first star. It's called a population 3 star, and it emits radiation. And so these halos are bathed in that. Okay. Happily, these smaller halos had molecular hydrogen in them, but they no longer do because they've been bathed by this radiation. So these would be great sites to form black holes. So all of these right at this moment can form direct collapse black holes, but oh no, because time passes and these are massive stars. They live for about 1 million years. So 1 million years later, there's a problem because that population 3 star will go supernova. And as soon as it does, it's ejecting metals into the universe. And these places here that would have been great for forming direct collapse black holes now can't, because they're metal enriched, and that means the gas is going to cool like that, fragment, and form stars. This one's still fine, except time passes and this dark matter halo grows. And if it grows massive enough, then there's enough sort of kinetic energy from the molecules moving around that they're dissociated. Great, except the atomic line hydrogen now can bump into each other enough that the atomic hydrogen is excited, and then when it de-excites, it can emit photons. So you have atomic line cooling here, and so now you can't form a direct collapse black hole here either, because the gas cools too quickly by atomic hydrogen means. So in fact, it forms sort of the first generation of stars in this halo. So basically only this one can form for, let's say a couple million years. And these can form for direct collapse black holes for about a million years. What this means is that we've got kind of a Goldilocks scenario, black holes can form only in particular places that are bathed by Lyman-Warner radiation only for a little bit of time, because pretty soon those very halos are likely close enough to the bathing source, the photon source, to be metal enriched, and then you can't form a black hole this way. So basically, this concept means supermassive black holes are rare, formed from direct collapse black holes. This is a simulation that shows this concept early on. It had a uniform radiation background, Lyman-Warner radiation background. And what you see are just little regions that could possibly form black holes. And this is a, box size unit. So this must be a large part of the universe. Apologies. This must be like a redshift 9. I think it must be maybe a couple 100 megaparsecs up to a gigaparsec in size. Sorry, I don't remember exactly how big that is. But those places in the universe that can form direct collapse black holes are here rare, too rare, in fact. So let me just tell you real quick, we did some work on this, and what we did was we went back into simulations, and instead of applying a UV background that's uniformed, we found all the places where there were stars, and we populated the stellar energy distribution, and we propagated it through the universe. So we had a time-dependent and spatially dependent radiation field with a Lyman-Warner background that could, spatially and temporally sort of match reality. And what we found is a whole bunch of surprises. But here's a little part of that simulation. This is going to be the Milky Way at redshift 0. And at redshift 5, you can see in one halo already there are 3 direct collapse black holes, which is a lot compared to theory, which says that at most 1 direct collapse black hole can be made and in a halo, but most halos don't have any. Okay, so we found a bunch of surprises, and that is that you can form a bunch of direct collapse black holes in a single halo. Here is the mass of a particular halo that can host direct collapse black holes in our simulation as a function of metallicity. And here's the low metallicity gas threshold that a piece of gas, a particle of gas in the simulation has to have in order to be able to collapse directly into a black hole. Okay. Here, these little diamonds are the median metallicity of that particular halo. And here's, I think, the 75th and 25th percentile of that. And so you can see that, there are a couple of halos that are overall low metallicity, but you can form direct collapse black holes in dark matter halos that are really high metallicity comparatively. And it's just the rare tail of the metallicity distribution in that halo that is allowed to collapse. I'll show you a picture. So here's sort of a better picture. Here's a zoom in of one of the halos. And what we're seeing is flux of radiation that can bust up molecular hydrogen, Lyman-Werner flux. And this panel shows metallicity, where the red is metal rich, and these are metal poor. Okay, so you're seeing stars here, black holes here, where the stars are emitting a lot of Lyman-Werner flux nearby. That's great, but there's enough Lyman-Werner flux here to be bathed and keep the gene's mass high. However, you're in a pocket of relatively pristine gas here. So it happens to be Goldilocks place in a particular halo, but there are enough of those in a halo to form several black holes. They can form in different places than we thought, at different times than we thought, in a wide range of halos. You can read the paper or talk to me about it, but the big deal is that we think doing a more realistic version of this theory of direct collapse black hole, implementing that sort of more realistic physics in a simulation allows us to recognize that direct collapse black holes may form more commonly than we thought. So yay. We're going to talk about now how supermassive black holes grow, and here's the basic idea. So we have the mass of black hole on the x-axis, redshift old, today, and here are formation mechanisms, right? Here are these direct collapse black holes. Here's those population 3 seeds, the first star seeds that we were talking about. The broad idea is that through mergers of these proto-galaxies, or mergers of stellar seeds, plus gas accretion, you can grow from these smaller black holes into the supermassive black holes today. Okay, we kind of got that from the Eddington rate, although the Eddington rate doesn't include mergers either. Here's a little simulation of that we did. It's one halo that will form the Milky Way at redshift 0, and we're looking at redshift 6. All I want you to see here is just gas falling in along filaments. These are low angular momentum material that forms sort of a disk, and that dissipates energy, and the gas falls into the black hole and accretes. We took a census of this black hole, of this galaxy and its black hole, and we said, well, how much of its budget is from that cold gas? And how much of it could be from hot gas? And we found a surprise. So, okay, here you go. This is the black hole mass, cumulative. It grows up to be about 10 to the 7 at redshift 4. And that's its total mass. Here is the total gas mass that falls in, and then we divided it into cold gas, or merger-driven gas, or hot gas, because that's what we wanted to learn. But the biggest thing I think we learned is that, look, 10% or less of the black hole is actually gas. 90% of the black hole actually grows from other black holes, which is great news for gravitational waves, because it shows that another solution to making large black holes can just be mergers of other black holes. So, big surprise. Oops. Warning, I already told you this, but I'll warn you again. Take every single simulation you've ever seen with a grain of salt, because the black hole growth depends upon the implementation of actually the gas physics. So these are just different ways of dealing with gas, not black hole physics. It's just gas dynamics. So this is one type of simulation. Here's another type of simulation. And by the end, the two black holes are at different places and with different masses, just because of the way the hydro is dealt with. So caveat there. And the black hole growth depends upon the feedback recipe that we used. I warned you about that before, but here it is playing out. Just really quick show you massive black hole, stellar mass of the galaxy it sits in. Okay, this is one implementation of feedback. Here's another implementation of feedback, and you can just see different masses here, especially that are showing up in terms of the black hole growth versus the stellar mass. Okay, so be aware that that is a big deal for us nowadays. And I told you that AGN feedback is sometimes overzealous. And when that happens in a simulation, get to see gas temperature here, you see that gas blowing out, then it stifles star formation. So you end up with stellar masses that are lower than they should be. This is dark matter, you're seeing it's not affected. This is big pile of explosions and feedback blowing out gas and allowing it to make fewer stars here. So folks are working on that. This was Illustris 1. We're not there. Folks have done Illustris T and G to try and address this exact problem, and they've done better. Okay, so we've warned you that black holes could be a problem. We've made black holes. We've grown black holes. Okay. And now, let me just tell you, those were single black holes. But the whole point of the pulsar timing array and other gravitational wave detectors are to detect binary black holes merging. So let's find a way to bring those single black holes together to merge and make gravitational waves. First step, galaxy mergers. So if each galaxy has a black hole in it and galaxies grow by merging, then the black holes will meet due to galaxy mergers, and the black holes and the galaxies will sink together by a process called dynamical friction. So I have here the separation of the black holes, and I'm using 10 to the 6 solar mass black holes as kind of my my fiducial black hole here. So separation is tens of kiloparsecs. Yes, I think so. 100 kiloparsecs, sorry. And the time scale is about 100 million years. Again, 10 to the 12 times larger than the black hole itself. Quick explain what dynamical friction is, sorry. It is caused by gravity, basically, a collective gravity response. Sorry, hang on. I think I'm seeing something from, would you like housekeeping? Oh, no, sorry, it's my hotel. No, I don't want housekeeping services today. All right, so imagine that you have a really heavy point particle flowing into a sea of stars. Well, what happens is this heavy particle goes into the sea of stars, which in the formalism is actually infinite. And stars are, their trajectory is bent, gravitationally focused, so that there will be an overdensity, high density, overdensity behind this moving particle. And as you can see, the velocity vector's fast, it's large when this particle enters, but this wake tugs that the point particle, let's just call it a black hole, tugs it backwards and slows the velocity of this moving particle. That's like a friction effect, but it's all caused by just straight up gravity, collective motion of gravity. Okay, so when this particle's really fast, dynamical friction just logically is low, And you can think about it because this particle moves too fast. And so the wake takes time to react. And by the time these stars have gravitationally focused, this black hole is long gone. When this black hole is basically standing still, dynamical friction is also low because there's a wake all the way around. Okay, so in the limits where this is moving super ridiculously fast or super ridiculously slow, dynamical friction is low. Here's the actual equation. Sorry, I have 2 Coulomb logarithm. Apologies. Okay, so this is the equation, and it's called Chandrasekhar's dynamical friction, this particular formalism. I have a set where we derive this. I don't know if you really want to watch it, so I didn't include it because also I'll be too late if we do. Anyway, this is the force actually it's acceleration, sorry, on the moving black hole. And it has to do with the mass of that black hole, the density of the sea of stars, the velocity of that black hole cubed, right? And this little Earth function here that has to do with the assumption that the velocity distribution of that sea of stars is Maxwellian. Probably isn't. I think that's fine. Cool. That's it. Oh, but assumptions. Man, there are a bunch of assumptions. First of all, the sea was infinite, isotropic. It was a constant density sea. M, the big M, is a point particle, never loses mass, never gains mass. The velocity distribution of the stars are also Maxwellian. And you're only dealing with this local wake. All those things are wrong. Oh, and this Coulomb logarithm is usually sort of approximated. It has to do with the impact parameter, or how close those stars, that sea of stars, can come to the black hole particle. And there's a range of those impact parameters, and this estimates that range. Again, it's called the Coulomb logarithm. Coulomb, because you'll see the exact same thing in Bremsstrahlung radiation when you talk about that in E&M. Okay, so further simplifications. If you have that point mass particle on a circular orbit, then you can approximate Chandrasekhar's formula, which already had a bunch of assumptions, like this. Okay, so that would be the force. Note it's m squared, big M squared, here, and it depends upon the time, the radius that you start, blah, 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 blah. The radius that you start the black hole. Thank you. We're talking about black holes. Sorry. Big deal is that the orbit remains circular. Here's the decay time right here. Okay, depends upon the circular velocity, the initial radius that you drop this in on, that Coulomb logarithm again, which is a number of order 10. Here are some typical sizes or typical values of a black hole, 10 to the 8 solar masses, falling into a typical galaxy, kind of a big galaxy, with a velocity dispersion of 200 kilometers a second. Vmax is about galaxy sized. Coulomb logarithms something. This time scale for this black hole to fall in from about 5 kpc is about 3 gig years. So a single black hole takes giga years to fall in from astrophysically large distances. But remember, the black holes in this case are dumped into a galaxy that is going to lose mass all along the way as it dynamically fricks, but is still quite massive. And so the time scale for bringing the black hole in to the center of the galaxy during a galaxy merger to meet the other black hole is much shorter because, again, the host galaxy that hosts that secondary black hole is shepherds the black hole in. Okay, So the black holes are now in the center of a galaxy. They're separated by tens of parsecs for Milky Way mass black holes. They're bound together as a binary system, and they then shrink the orbit because of three-body scattering. So there'll be a star that comes in, it'll interact with that binary black hole. It will bleed away energy and angular momentum, taking it away, maybe scattering the star completely out of the galaxy, and that makes the two black holes shrink closer, the orbits shrink closer, the orbit faster. That happens at something called a hardening radius, which again is about 10 parsecs. And the time scale for this, the black holes to shrink to the next stage, which is gravitational radiation, is infinity, basically. In the case of a static galaxy model that is perfectly spherical, and once the black hole, the star scatters, it leaves forever. So really super simplified case. And that was called the final parsec problem. Oh, I'll get to that. So this is a cool example of three-body scattering. It is not black hole and star. These are more equal mass. But as you can see, here's a bound system, 1 and 2 black holes orbiting around one another. Third black hole comes in, mess, because three-body and the three-body problem is chaotic. There are a couple stable solutions, but not always. 1 gets flung out, and there's an exchange. 3 now joins with 2. You have sort of an eccentric orbit here. And because of that interaction and the fact that this is more eccentric, the gravitational wave time scale is a lot shorter because the system has gotten closer and more eccentric. So that process in general is what happens, except the mass ratio between 1 and 2, 1 plus 2 and 3 is very different. And this three-body scattering phase all depends upon how many stars are really available for those black holes to scatter. The region of phase space, energy and angular momentum space, that contains the stars that can interact and get flung out from a black hole or a black hole binary is called the loss cone. Okay, this is a representation of the loss cone. So you've got angular momentum here, weighted by circular angular momentum. So this is a radial orbit, and this is a circular orbit, and these are all stars that are on that. And this is energy far away from the black hole, less bound to the black hole, and more bound to the black hole, aka closer to the black hole. Normally there would be stars all over here, and there are. But after you run a simulation for a little while, all these stars have interacted with the binary and they're flung out. So this loss cone is evacuated pretty quickly, and thereafter there's no more stars here that could interact with the black hole, because it takes over a Hubble time for stars to diffuse naturally from here to here. Okay, so refilling the loss cone in a spherical static model takes forever. These stars right here just happen to be stars that weren't kicked out totally, so they'll come back and they'll interact. But see, there's not that much. This is that hardening radius that we spoke about, and you can see even after the hardening radius, there's a lot of stars that are still still have interacted. So it's not, the loss cone isn't perfect, but you can see here at the loss cone, you've killed all the stars. Okay, so if you have thrown out every possible star that this black hole binary can interact with, there's no more stars to interact, to take energy and angular momentum away from the system, so the binary black hole stalls. It cannot get any closer, okay? And it just so happens that for this case of a static spherical system, the black holes are too far apart for them to get close, for them to for gravitational radiation to take over and be strong enough for the black holes to merge in a Hubble time. So This is called the final parsec problem, which is refilling that spherical lost cone takes over a Hubble time. And I am going to tell you that's fake. It's a spherical cow. And there is no problem with stalling, because once you make a more realistic galaxy, then the orbits in that galaxy are totally different, and they will refill the lost cone much faster. Okay, so here's some early simulations that just kind of show this. Here are two black holes, and when the system turns sort of triaxial, black holes are in this galaxy. The galaxy system turns triaxial and the black holes merge. And then we did this for a very static case. We said, let's not make a merger. Let's just set the galaxy here and just let the orbits do their work. And in the most gentle case, where the system is static, it's non-spherical, it's not rotating, the 10 to the 8 solar mass binary black holes will take about 3 gigayears to coalesce, which is still a long time. But again, we've gone from perfectly idealized to still really idealized, but only slightly less idealized case. Galaxies are not like this either. The reason why, again, is because you get these special orbits that don't have to conserve angular momentum. This one does, but in this case, you get black holes. This is X and Z side view of an orbit, top view of an orbit looking down, and you can see they're pretty centrophilic. These types of orbits like the center of a system. And so there's plenty of times where this type of black hole, this type of orbit will interact with the black hole. Even better, I don't think I have pictures of them. Shoot. Triaxial systems have orbits that don't conserve angular momentum at all. And some of them will look like, I'm going to draw here, some of them will look like this fish, and they'll go back. What? So y'all know orbits that just do this, right? This is kind of like that. This orbit in a triaxial system starts here, moves back, stops, and goes backwards. So talk about not conserving angular momentum. It can go formally through zero. Orbits in triaxial galaxies can formally go through zero, formally feed a black hole. But in this axisymmetric system, you get similar types of orbits, and they refill the lost cone. You can make black holes rotate, and if so, the orbits shrink faster. This is a plot that's not so great to talk about, but time. And this is 1 over the separation. So really, you're looking for something here being really close together. Sorry, it's just the way this field does it. And right about there is, in these units, the place where the gravitational radiation starts to dominate, and then the black hole can merge through gravitational radiation. So you've got to get up to here. And spherical galaxies just don't have the black holes get close enough for 3-body scattering to pass the baton to gravitational radiation. If you have this flattened, non-rotating axisymmetric system, you solve the final parsec problem. And if you let this system rotate, then it's even faster. The two black holes shrink even faster. So we've done a suite of simulations of varying types of galaxies, each more realistic. And we can have black holes merge, on timescales of 3 gigayears, which we don't think is realistic because galaxies are not static axisymmetric things that don't rotate and never change. Okay, so this is kind of an upper limit. And we can have 10 million years for galaxies that are triaxial, and the eccentricity changes dramatically. in the gravitational wave regime. So look for this to be sort of a growing area, so that folks can start to populate galaxies with more realistic black hole merger timescales. And then, as you know, once the black holes get close enough, on this timescale of like an AU, couple tens of AU, then gravitational radiation dominates. And oh, sorry, that was a joke. It was because computational physics couldn't merge black holes a long time ago. Never mind that. Then the black holes merge. Oh, except I'm going to skip this. This is called gravitational wave recoil, and it just says that when two black holes are perfectly symmetric, then the gravitational waves that are emitted are perfectly symmetric. But if there's any difference, like a difference in mass ratio or something, then the gravitational radiation that's emitted is preferentially on one side, and so you get a kick, a recoil kick, and that kick can be fast. And so here is an example of maybe two black holes that have merged, and that new black hole gets kicked at a velocity that basically removes it from a galaxy. So here's an example of that possibly happening. Black holes merging and then gets kicked. So that's artist rendition, obviously. These are the two black holes, one of which is moving super quickly. So an example maybe of a recoiling black hole. Okay, so I've just talked about a bazillion things. I've talked about at a super fast rate, sorry. We spoke about how supermassive black holes existing really early on is a bit of a problem, at least on the back of the envelope calculation. Because if you happen to have a black hole that accretes forever at the maximum rate that a spherical system allows, with a canonical conversion between luminosity and between mass infalling and luminosity, then there's not enough time in the universe, or barely enough time in the universe, to grow a black hole as massive as what we see. Again, there's a ton of ways to make that not a problem by just assuming any kind of break in symmetry or any kind of relaxation of any of the assumptions that we made, like faster than Eddington accretion. It's really easy to do. So I think that that's actually the answer. But nonetheless, as we see more and more black holes at higher and higher redshift, we'll have to revisit every assumption we've made. Okay, so we talked about how black holes grow through mergers and accretion, mergers early on, and accretion sort of throughout, more accretion towards redshift 0. We talked about how black holes are born, specifically direct collapse black holes, because they're more likely to make supermassive black holes because the seeds are massive to start with. We said that contrary to popular belief, this direct collapse black hole scenario may be more common than people theorize. People theorize you make one at most direct collapse black hole per halo in a specific range in time. But if you relax some of the assumptions that people make to simplify the models, you can make more direct collapse black holes than we thought. Nonetheless, we still have a lot of work to do to understand that black hole formation scenario, definitely. And then we talked about black hole dynamics. So how you get single black holes in each galaxy to come together and merge. We talked about dynamical friction and all the simplifying assumptions that go into that. We talked about three-body scattering and the final parsec problem and all the simplifications that go into making that a problem when it really isn't. And then we said the words gravitational radiation, and then I mentioned recoil really quickly. That was a lot. If you have questions on any of that, please ask. I could talk about these kinds of topics all day. And, you know, if I don't know the answer to something, uh, don't worry, I'll investigate it. We'll investigate it together, and we'll both learn something. So thanks for your attention. And I hope to see you sometime this week. Take care. Bye.